Okay, so we're going to talk about structured concurrency in Java, specifically what it is and why it is important. Okay, so let's get started. I'm Balkrishna Rawool. I work as IT chapter lead at ING Bank. Project Loom. Okay, so Project Loom is one of the most important projects at OpenJDK, and the purpose of Loom is supporting easy to use, high throughput, lightweight concurrency, and new programming models for it. So the focus is a lot on concurrency, specifically on lightweight concurrency, also something that gives high throughput and which is easy to use. Okay, there are three main features in this: virtual threads, structured concurrency, and scope values. The focus of this talk is going to be about structured concurrency, and in order to get there, we'll get a little introduction of virtual threads, but scope values are out of scope. We'll not discuss that. Yeah, the status as of now, so what is envisioned for Java 21 is that virtual threads will be finalized, so they are out of preview. Structured concurrency and scope values will be in preview. So a lot of the code that you will see, yeah, you can use it with the early access builds of Java 21. And the talk will be roughly divided into three parts. So we start with virtual threads first, and then we'll go a little deeper into structured concurrency. And at the end, we have some examples where we compare CompletableFuture API with Structured Concurrency API, and that will be the biggest part of this talk. Okay, to start with virtual threads, we have to go to first platform threads. So platform threads are the traditional threads, which we know as threads from Java 1.1. And they provide an abstraction over operating system threads. So what that means is if your application requires a new thread, that application has to go to OS and ask for a new thread to be created. Now, OS threads are, let's say, resource intensive. They take a relatively large amount of memory, and also it's a rather slow process to create a new OS thread. And therefore, what happens is that if you use thread per request model for your application, it might provide you limited scalability. So because there are so many number of threads you can create, and therefore, if you are using thread per request, meaning if a new request to your application is creating a new thread to process it, then you will have scalability, which would be still high number of threads, but let's say limited. And because of the nature of the platform threads that they require so much memory, and also it is a resource-intensive task to create them, we tend to pool them. So we put them in pools where you don't have to create them again, once they are requested, so you can take them from the pool. Virtual threads, on the other hand, are lightweight user threads. Lightweight because they require significantly less memory than platform threads. And because they require so less memory, you can just create them in abundance, so thousands or even millions. That makes them highly scalable. Also, they don't really require your application to go to operating system. And there is no need to pool them because they are cheap. You can just create them whenever you need them, and you can just throw away when you don't need them. But okay, how do you create a new thread? I think you all probably have done this, at least in your example applications where you create a new thread by passing a runnable to it. So in this case, let me just print the current thread. Right, so if I start this thread, yeah, okay. So if I run this method, so actually how do I run it? I have a JUnit which just executes this. This is not really a JUnit test, but it is just a wrapper to run this method. So if I run this, this creates a new thread. Okay, with the new thread API, you are still able to create new thread by using thread.offPlatform.start. So that also takes runnable. You don't need to call the start explicitly. So if I run this, you'll see the same thing. Basically, it creates a new thread. Now, how do we create virtual thread? You probably would have guessed from the previous call. So you do thread.offVirtual, and then you do start. again, pass it a runnable, and I'm going to do the same thing, thread.current thread. Okay, if I run this, we will see a, sorry, I ran the wrong method. So if I run this one, you will see a virtual thread being created. Now, there is more. There is more to this API. So there is also a shorthand method. So you can just do thread.start virtual thread. Does the same thing. And you can also use an executor service. Well, so if I use a new executor with executors.new virtual thread per task executor, so this will basically create a new virtual thread every time you request it, so there is no pulling involved. And I can do the same thing. So use the executor.submit, and that creates a new virtual thread. It takes a runnable, so I can basically just do the same thing. And that is exactly same as doing the earlier operation. I can have multiple of them. So if I see here, then I get multiple virtual threads. And basically, as I said earlier, they are lightweight, so you can create thousands or millions, but we're not going to do that right now. Presentation. Okay, let's continue. And I think I will have to end the presentation mode every time I switch to code, but okay, we'll do that. Okay, so what we see here is you have a bunch of virtual threads which are connected to one platform thread. What that means is a virtual thread on its own cannot execute anything, so it has to be associated with a platform thread to execute something. And that process is called as mounting a virtual thread onto platform thread or carrier thread. So, and that is being done by a virtual thread scheduler, so there is a specific scheduler for it. What that does is, if a virtual thread requires platform thread, it mounts that onto the platform thread. And when it does not require platform thread, for example, if there's a blocking operation being carried out and the virtual thread is just waiting, then it unmounts it from the platform thread. And that mounting and mounting is done by a virtual thread scheduler. And it uses a dedicated fork join pool. That's why in the example here you see fork join pool being used. And what you see in the IDs of these virtual threads is that this is the virtual thread ID, and this is basically the carrier thread or the platform thread that it is using. And one interesting thing that we see here is that, because I created 3 of them, you see the first virtual thread is using this platform thread, worker 1, but the second. Oh, yeah, I have to end the slideshow, switch to code. Okay, so what you see here is that we created 3 virtual threads. And this part is the platform thread or the carrier thread, and this part is the virtual thread. So this is basically an ID which puts both the IDs together. What we see is that the first virtual thread is using one platform thread, but the second and third virtual threads are using the same platform thread. So that's what basically having multiple virtual threads being mounted and unmounted from the same platform thread. Okay, let me go back to presentation mode. So yeah, here you see another example where you have 4 virtual threads, and basically they are, let's say they do some processing, and then they have some waiting time. The waiting time is represented here in gray, and the processing is done in green. So what you see is that there is some waiting time, some processing time for all 4 of these, but the way their processing is done, they are able to basically utilize the same platform thread this way. Typically, the gray part is like really big because that's imagine a network I/O that requires hundreds of milliseconds, and the green part is really small, like some nanoseconds. So you can imagine the scale of, let's say, waiting time is thousands or millions of times bigger than the processing time. So a platform thread can basically handle thousands of virtual thread, and that gives the high scalability part. So how do you use virtual threads? You use virtual threads to model your tasks, right? You don't use them as platform threads because they are easy to create, like they are cheap. So you basically, the best way to use them is to submit a task or a business task to it, and you can put these tasks together and you can structure them in, let's say, logical way that your business requirements depict, and that would be the, let's say, best way to use virtual threads. Also because that would represent your business logic in the, in an easy to read way. Now, the way of structuring these tasks or virtual threads is called a structured concurrency. So that's how virtual threads enable structured concurrency, right? With platform threads, you still have to think about how are you going to manage your pools. But with virtual threads, you can only focus on your business logic, create virtual threads for your business tasks, and structure them in the most logical way. Structured concurrency as a term is also inspired by the term structured programming. So the way structured programming brings in clarity or readability to your programs, structured concurrency brings in that readability or clarity to your concurrent programs, right? So what structured concurrency is to concurrent programs is what structured programming is to programs. A little bit more about structured concurrency. So the principle is that when a flow of execution splits into multiple concurrent flows, basically executing multiple subtasks, they rejoin in the same code block. So what we see here is that you have this first green arrow, which basically represents part of the main task, and that splits into multiple subtasks. And in this case, we want all of these subtasks to be finished at the same time in order to continue with the main task, right? And the benefits of structured concurrency are that you get error handling with short circuiting. So in this case, if your, let's say, first task gets some error, you don't really want to continue with the other two subtasks, right? Because you want results of all of them. So they are immediately canceled. Again, cancellation propagation, what that means is if you have a parent task, which is creating subtasks, and if the parent task gets canceled, it gets propagated to the child task as well, and they are also canceled. That is all being done by Structured Concurrency API. Clarity, because your code represents exactly what you want from your, let's say, business requirements, the way the logic should be. So that clarity comes to your application, and that makes it more readable. Also, observability. So if you see here, you always have like parent task, subtasks, and their subtasks. So it's a big hierarchy of tasks, basically big hierarchy of virtual threads, right? And when you do a thread dump, that exact same hierarchy is put into your thread dump. So that way, you get a good overview of what is happening with your threads, and you can pinpoint to a particular thread if that is going wrong. Okay, a few more examples. So this is what we saw earlier. You have one main task, 3 subtasks. You want all of them to be finished. You can also organize in such a way that you want only one of them to be finished, right? And then you don't wait for other subtasks. Or you can also have nested, nested tasks or nested scope. So you start basically with, in here, you start with these 3 subtasks. You wait only for the completion of 2 of them, and then you start a 4th subtask, and then you wait for the 1st and the 4th to continue with your main task. Now, all of these examples can be modeled using structured task scope, and that is what we will see later on with some code examples. So what we will do is we will basically get a few examples. We will implement them using CompletableFuture API. Then we will implement them using Structured Concurrency API, and then we will do a comparison of how it looks, right? So a quick recap of or revisit to the CompletableFuture API. It provides an API for asynchronous processing. So it's a very powerful API which allows you to chain multiple stages and then create these pipelines. And it relies heavily on callbacks because of the asynchronous processing. So what we will do is, as I said, we will basically compare them head to head with few examples. So let's start with the first example. So here what you have is you want to create an event. In order to create that event, you need to reserve venue, book hotel, and buy supplies. When all of these subtasks are finished, you are able to create your event. Right, so let's go back to IntelliJ, and I have to remind that I have to end my slideshow. go to IntelliJ, then open CompletableFuture examples. And yeah, so this is the first example. What you see here is you have create event method. And that is basically creating three completed futures, each for one task. So these are venue, book, hotel, buy supplies. And when these three, and then these three futures are combined using all of, because you want to finish all of them. Do some exception handling, and then basically in a callback, get their results and create your event object. What's happening within these event util is not that exciting. It's just basically log and wait. So yeah, it is to simulate the fact that there is some blocking operation happening, and log and wait is waiting for a random amount of time. It also prints which thread it is getting executed on. It says the task is done when it is done. So nothing really fancy. Okay, so let me run this. And the way to run this again is to have JUnit. So I have some JUnit tests which are just wrappers around these methods. If I run the first one, yeah, this one, then what should happen is these three subtasks should get started. When all of them finish, then your event should get created. Yeah, so what you saw is these platform threads are being created, and they are used to execute these tasks. When all of them are finished, you have your event object. Now, how do you do that in Structured Concurrency API? I have this class Loom examples where I'm going to implement these methods. So basically, you always start with try with resources because the scope object that you create is auto-closable. So it basically, at the end of the try, it frees up resources when they're not needed. And structured task scope is the, what do you say, sort of the main API. And it has two subclasses, shutdown on failure and shutdown on success. In this case, we will use shutdown on failure because we want all of the subtasks to be finished. So basically, shutdown on failure means that you shut down when there is a failure. And when you want all of your subtasks to be finished, you basically want to stop when there is a failure, because it doesn't make any sense to continue. You want all of them to be successful. When there is one failure, you stop, you cancel everything, and say there is something wrong. Right? So we use shutdown on failure in this case. Because we have these subtasks and we want all of them to be finished. And what do you do with the scope? You fork some tasks from there. So that will create a virtual thread. And I can just basically copy paste these subtasks here. Yeah. Okay, so each fork method gives you a task, actually an instance of a class called subtask, and you can get a handle on that, and which will be useful later. So let me just do that. And then what do you do with this scope? You basically join, because you want to wait for it to finish, and then join throws an exception, which is interrupted exception. And if something goes wrong in this whole operation, you want the errors to be propagated, so you do that by using throw if failed. Throw if failed also throws an exception, and we can catch that as well, right? Okay, what do you do with the scope then? Now you want to get the results of your subtasks. So in this case, the first task will give me venue, and the other two subtasks will give me hotel and supplies, and then I can use them to create my event. So if I just create a new event, I can pass venue, hotel, supplies to it, and that should be equivalent to the CompletableFuture example. Okay, so when I run this, it should behave exactly the same as the other example. The only difference being it will use virtual threads instead of, and they all take 7 seconds, so they all should be done at the same time. Okay, so you have your event object. Okay, now let's do a little comparison. So what we see here is that the CompletableFuture relies on callbacks. So you always have this then method, so then apply, then accept, and then you basically do your processing within these callbacks. That's That's the nature of CompletableFuture API. Whereas in structured concurrency, you do it sort of imperatively, right? You create your subtasks, you join them, you get their results, and then you continue. Other difference is that here your exception handling relies on runtime exceptions. I think CompletableFuture throws completion exception, which is a runtime exception, whereas in structured task scope, you get execution exception, which is a checked exception. So you basically have to handle the error scenarios. You can't escape. I think it's nice. Yeah. What else? Yeah, one small difference or one small quirk about the all of. Yeah, it gives you a CompletableFuture of void. Basically, that means you have a useless parameter that you have to deal with. I mean, nothing really big, but that's a small quirk of all of method. Okay, so that's about the first example, and we have more example. I'm not going to switch to the presentation mode, but let's get the second one. So here you have 3 subtasks, and you want to just get the results of any one which finishes, right? So what you have here is you want to get weather, and you have 3 different sources. You basically ask all of them at the same time, and whichever gives you answer first, you just use that. How will you do with CompletableFuture? You basically have these 3 CompletableFutures for your 3 subtasks, and then you use any of, because you want, well, a new future which should finish when any of the underlying futures finish it. And then you do some exception handling, and then you basically get your result. Right? Let me run this and see if it works the way we want it to work. And it does. So basically, you have these 3 platform threads taking some time, and the first one I think finishes really fast in 0 seconds. So you get the result from source 3, and whether it's going to be 27 degrees. Let me do the same thing with structured concurrency. So again, you start with try with resources. You have a scope object, which is nothing but a structured task scope. And in this case, we'll use shutdown on success because we want to stop when there is success from one of the underlying subtasks, right? It takes a parameter, which is going to be the type of the result that you expect. So in this case, we are expecting weather, so we will use weather as the type. And then again, something similar to what we did earlier. So you use scope.fork, and then you fork your subtasks. Let's get the runables from here. So yeah, so you get the result from the first source, and then you get from the second and third. And then you basically join. You want to wait until one of them finishes and handle the exception. And in this case, you immediately get the result from the scope itself. Right? So, and then you can basically use it in a variable, and let me just print that. So this should behave same as the CompletableFuture example. Right, it does. So in this case, source 1 finishes fast, and you have your weather. Okay, now let's do a little comparison. Besides the asynchronous nature of CompletableFuture with callables, and the fact that the exception handling is with runtime exceptions, what else do you see different? I mean, yeah, one small little thing. Any of gives you a CompletableFuture of object. Although all of these futures will give you weather, it's a bit strange that this gives you an object. So basically, this weather is just an object instance and not a weather instance. Whereas in this case, when you do result, you actually get weather object. So this weather is an instance of weather class. And okay, now I'm going to ask you a question. So you have here 3 subtasks, right? What happens one of them, let's say, throws an exception or fails? So throw new runtime exception. Although one of them fails, but there are two which would eventually continue and be successful. How many of you think that this will result in an error? Okay, there is one person, 2, 3, 4, 5. That's probably, say, 10% or maybe less than 10% of the audience. Well, you guys are right, because if I now execute this, oh, not that one. Yeah, so it's a bit strange to have your resulting future give an error when you know that one of them is going to be successful, or which might become successful, and you stop at the first instance, you get an error. Now, with the same setup, what do you think will happen with CompletableFuture or Structured Concurrency API? How many of you think there will be an error? None, because the talk is about structured concurrency, so of course it's not going to be an error. So yeah, you see two of the subtasks because you don't see the one which throws a runtime exception. And well, because they are both finishing at the same time, you see both of them finished here. So only one of them is used to actually get the result, but the error is ignored. Let me run it once again just to be sure that it's actually using one and canceling the other. So in this case, you have to wait for 7 seconds, and then you will get output from one, and yeah, source 3 and not from the source 2. So I think it's a bit more logical this way, although it is still fine as long as you know what's happening underneath the API, and you can handle it, deal with it. But yeah, I think it's more logical the way Structured Concurrency API behaves. Okay, now the third example. So what we have here is a banking portal. And you first get the customer data. Then you have to wait to finish 2 of your subtasks to get savings and loans data. And in the end, you calculate offer. Apparently, the customer is waiting for some offer, and this is how you do it. So how will you do that in CompletableFuture API? Yeah, so you create first a future of your subtask, which gives you customer. Then you basically start these 2 other futures in an async fashion, because you want them to be doing things at the same time concurrently. And you wait for the first one to finish, and then you combine future 2 and future 3 with the results of future 1, and then you get some object. You use that to calculate offer, right? So this is how the implementation will be. Let's see if it works the way we want it to work. Okay, so first we are getting the customer. Takes 4 seconds. Then we have 2 subtasks to get the savings and loans data. Once we have both of them, we calculate offer, and then you have the offer object. Okay, how will it look like in Structured Concurrency API? Yeah, you always start with try with resources, right? Okay, so what we're going to do inside this, we are going to call this subtask, which will get the current customer, right? But this is the only operation that we are doing. We're not actually orchestrating multiple subtasks, right? So do you really need a scope around it? No, you can just be done with it by using one, let's say, virtual thread. So you can just simply do thread.virtual start, and then you can write your logic to get the current customer here. Okay, but imagine a scenario where your application is deployed in a server, which by default creates virtual threads, right? So let's say your Tomcat is creating virtual threads every time there is a new request. So you are operating in a virtual thread context. Then you don't need to create a new virtual thread, right? So in that case, you could only do this, and that should be sufficient. Right? In order to simulate that environment, what I have done is basically I create a virtual thread inside the inside the JUnit test, and so that simulates the environment where you have your web server creating virtual threads to process your requests. And then, okay, we have our customer object. Again, the interesting thing about this is that this is a blocking operation, and although it is blocking, we don't care because it's virtual thread. It will get unmounted when there is blocking, let's say, blocking operation, and when you have result, it gets mounted. So we don't really have to worry about whether you're calling blocking or non-blocking, and let's just continue with the result. So you have customer now. Then you have to execute these two methods. So you use, again, try with resources. You create your scope, and in this case, it's going to be structured task scope, shutdown on success or shutdown on failure, because you want both of them to be finished. Failure, yes. So and then you have scope.fork, and then you fork your subtasks. Yeah, in this case, we can't use method references. That's the only downside I have seen so far, but you have to explicitly call because you are passing the data to it, which it doesn't have yet. Okay, and then you get the loans data, and these are two subtasks. Okay, and then you join the scope, exception handling, and exception propagation. Okay, so task 1 will give you savings, and task 2 will give you loans data. Okay, what do you do with that? You will create a details object, apparently. So new customer details with customer savings and loans data. Okay, what do you do then? Now you have to call calculate offer, which is again going to be blocking. It's good to call it with a scope around it. So you have your scope. You can also create a new scope inside that. So let's just say we create a new scope where try scope 2. And it would be fine to do that. But there's also an interesting thing about scope that you can reuse it. So when you fork your subtasks and you join them, you can reuse the same scope to fork again. So you basically can do scope.fork, and then you can fork the calculate offer subtask. And pass details to it. Oh, has to be lambda. Okay, and then this will basically give us a task 3. Yeah, don't use these variable names in your actual code. Use more logical names. This is just for example. Task 3 will give us an offer. Okay, and then you can print your offer. So let's just run this. Get offer. And this should behave same as the CompletableFuture one. So you have your customer, then you are running your subtasks parallelly. Oops, that is an error. Oh yeah, of course you have to join, and so you wait and then you propagate the errors. It's good to find the errors in your unit test, right? Okay, so again, wait for customer and then savings and loans data. Once you have them, you do the final subtask calculating offer, and this looks similar to what we had with CompletableFuture. Okay, one small thing, you actually are doing one operation here. You really need a scope? No, right? You're not orchestrating anything. So why not just do our offer here, just like that? It's blocking. We don't care. Okay, so let me run this. And this should, again, behave the same way. And it will. Let's wait it to finish. 8 seconds. The next thing we'll do is we will compare these two implementations. Okay, so let's look at CompletableFuture example. So what I see here is, you had this picture, right? And the picture is not really clear from here. So you actually have to read this code, then form a mental model of what is happening with these subtasks, right? And then use that mental model to continue reading code further. Whereas in whereas in structured concurrency, you basically get the structure of your subtasks right from the code. So you see that you have you basically get customer, then you fork some subtasks, you wait for them, and then you basically continue with more tasks. So that's the advantage with structured concurrency API, that your business logic becomes really clear and it's easier to read. Okay, I have one final thing to show you, and then we go back to the presentation. So here, the structured concurrency API, it says you fork your subtasks and you join them, but who's stopping you from just joining without creating subtasks, right? So you can just, let me just comment these things out. What do you think will happen here? So you're joining, you're saying we want to wait or we want to shut down on failure, but there are no subtasks. Okay, let me run this and see what happens. Oh, there's error. Okay. So it runs fine. Why? Well, we are saying that you will shut down on a failure, or you will basically say there is something wrong when there is a failure, but there's no failure happening here. Although there are 0 subtasks, all 0 subtasks have finished successfully, so there is no problem, right? So, if you look at it in a way, it's still logical. Now, what do you think will happen in this example when you do the exact same thing? So you basically comment these, and the compiler doesn't complain here, right? The compiler is even fine with you getting the results from your scope. So what's happening? Now what do you think will happen? Success, error? Okay, those who are saying error are the winners. Yes, it does give you an error, thankfully so, because you can't have results when you don't have any subtasks, right? And if you see here, the exception is being thrown by result and not by join. So join is happily joining because there are 0 subtasks. But when you actually want a result, there is an error. So that's how let's say there are some quirks from the structured concurrency API as well. This was probably the last thing to show. Go back to the presentation. So shutdown policies, as we saw, there are 2 shutdown policies: shutdown on failure, shutdown on success. So you use the failure one when you want all of your subtasks to be finished. So in that case, it cancels when there is failure. And shutdown on success, you will use it when you want one of the tasks to succeed, right? And it cancels the other task when there is success on one. You can also create custom shutdown policy by extending the structured task scope. So like you create one more subclass as shutdown on failure or shutdown on success. You override the handle complete method. So that's the handle you have on basically dealing with what is happening with the successes or failures. And you can use it to write your custom logic. You can, let's say, shut down on completion of some tasks successfulully or in failure mode. So that's, you can just do whatever you want. We're not going to see that example because I don't think we have the time. One thing to be really aware of while dealing with virtual threads is pinning. So when your virtual thread is executing a synchronized code block or a synchronized method, the virtual thread gets pinned to the platform thread. What that means is that the virtual thread cannot be unmounted from the platform thread. And if that is happening, I mean, there is no benefit of using virtual threads, right? Because your virtual threads will behave same as platform threads with the extra overhead of creating these virtual threads. It is only a problem if you are doing long-running or blocking operations inside your synchronized code, because if it's just like, let's say, finishes quickly, then the pinning happens only for a really short period of time and your application won't notice it. But if you do have these cases, you can identify them with JFR, the JDK flight recorder, and then you can replace your synchronized logic with reentrant lock, and that should basically solve it. That's it. And